अस्सलाम वालेकुम। जैसे कि आपको मालूम है कि हमने अपने कोर्स का थर्मोडायनामिक वाला पार्ट ख़त्म किया हुआ है और स्टैटिस्टिकल मैकेनिक्स का पार्ट हमने शुरू किया था। और छुट्टी से पहले हमने स्टैटिस्टिकल मैकेनिक्स के हवाले से एक इंट्रोडक्टरी लेक्चर लिया हुआ था, लेकिन अब चूंकि बहुत सारा टाइम हो गया है तो मैं चाहूँगा कि वो चीज़ें हम दोबारा से रिवाइज कर लें। So, when we talk about the thermodynamics, so in thermodynamics, we discuss the experimental laws which determine the macroscopic behavior of the system. Then we also studied the kinetic molecular theory, and in this theory, we discussed that the macroscopic behavior of the system could be associated with the microscopic behavior of the molecule of the system. So in statistical mechanics, the approach is in the reverse order of kinetic molecular theory, that it associates the microscopic behavior of the molecule of the system to the macroscopic behavior of the system. That is, we have the macroscopic behavior are represented by the macrostat, and those macrostat are found in terms of the thermodynamic laws. And the kinetic molecule theory connects those macrostats to the microstats. And when we know about the microstat in terms of the laws of statistics, so we can connect those microstat to the macrostat by using the statistical mechanics. So the job of statistical mechanics is to connect the microstat with the macrostat, or to find the macroscopic properties of the system by the microscopic properties of the system. Okay, so when you start a new subject, so you must know about the terminology of that subject. And we know that the statistical mechanics applies to the atoms and molecule, and the behavior of atoms and molecules fall under the subject of quantum mechanics. And one of the important aspects of quantum mechanics is the quantization of energy. So here we will talk about the discrete energy level, for example, Ej, that could be equal to E1, E2, E3, and E4. So here we have a system in which we have different energy level, E1, E2, E3, and E4. And the energy are discrete, so that is why the total energy will be found by the summation of all the energies of the particle. Another important term is the degeneracy. So degeneracy is the number of energy state in a particular energy level, and it is represented by Gj. For example, if we say G1 is equal to 1, it means there is one energy state in the energy level E1, and if G2 is equal to 3, it means there are three energy state in the energy level E2. So the energy state are represented by these boxes and different energy levels. So the energy level are represented by these horizontal line, and the energy states are represented by the boxes in each of these energy level. And then these boxes are designated by the numbers 1, 2, 3, 4, and 5. So when we talk about the energy state 1 and the energy state energy level E2, for example, so we mean this energy level. And if we talk about the energy state 3 and the energy level E4, so we talk about this energy state. So these are designated by 1, 2, 3, and 4, and so on. So we have another important term, the microstate, and this is the discretion of particle in the energy state. For example, the microstate of the energy level E4 could be represented by describing which energy state is occupied by how many number of particles. For example, the microstate of this E4 is no particle in state 1, no particle in state 2, one particle in state 3, no particle in state 4, and one particle in state 5. So this description represent the microstate of the system. We have another important term is the occupation number, and it is represented by Nj, means the number of particles in the jth energy level. So here, for example, we have 5 particles in the first energy level, so N1 is equal to 5. We have 4 particles in the second energy level, so N2 is equal to 4. So the total number of particles will be the sum of all these occupation number of the J levels. Then we have another important term, the macrostate, and this is the description of the particle in the energy level, and this is represented by the occupation number, that how many particles are there in each energy level. For example, the macrostate for energy level E1 is N1 is equal to 5. The macrostate for energy level E2 is equal to is N2 is equal to 4. And this should be kept in mind that for one macrostate there could be 1, 2, 3, 4 different microstate, and there are different macrostate in a single system. So we have an assembly of the microstate in a single macrostate, and we have an assembly of the macrostate in a single system. And we consider only those microstates for describing the macroscopic behavior of the system which are consistent with the observed macroscopic properties of the system. So those microstates which do not explain the observed macroscopic property of the system could not be included in the assembly of the macrostate. When we talk about the microstate or macrostates, so this is actually associated with the distribution of particle. And if the distribution of particle among the energy state of a system are known, so we can determine the macroscopic properties of that system from the distribution. For example, if we consider an atom as a system, and there we have the distribution of the electron among the different energy level. For example, in this distribution we have 2 particles in the first energy level, 8 particles in the second energy level, and the third level is empty. So if we consider this atom, so here we have 2 particles in the first energy level, 7 particles in the second energy level, and 1 particle in the third energy level. It means the distribution of particle in this atom is different from the distribution of particle in this atom. That is why both of these atoms have different property. So a particular distribution actually corresponds to a particular property of the system. So when we talk about the distribution of particle, so the distribution actually depends on the nature of the particle. So there we have 2 types of particle, the distinguishable particle and the indistinguishable particle. The distinguishable particles are those which we can be differentiated from each other on the basis of their mass, charge, or spin, or some other intrinsic properties. However, there is another aspect of distinguishing the particle, that is their position or trajectory. For example, if you have an amorphous material, so the molecule distributed there are randomly, and we cannot differentiate between the 2 molecules on the basis of their position. However, if these molecules are distributed in a crystal, so we can differentiate between the 2 particles on the basis of their position. So when we talk about the distribution of the particle, so we have to take care of the distinguishability and indistinguishability of the particles. So here we have the distribution of particles in the energy level and different energy state. So when we talk about the macro state, so actually we talk about the specification of the number of particles in each energy level. For example, if we talk about the macro state of this system, so we say that there are 5 particles in the energy level E1. There are 4 particles in the energy level E2. There are 3 particles energy level uh, E3, and there are 2 particles in the energy level E4. And when we talk about the microstates, so this is the specification of particle and the Gj energy state of the jth energy level. So for example, in the energy level E4, there is one particle in each of the state 3 and 5. One particle in each of the state 3 and 5. So in 3 and 5, and there is no particle in the state 1, 2, and 4. So 1, 2, and 4 are empty, and there is one particle in each of the state 3 and 4. So this description is known as the microstate of the system. And the overall description that how many particles are there in different energy levels. So this description is known as the macro state. However, we have two types of particles, the distinguishable and undistinguishable. So the undistinguishable particles are generally represented by the dots, and the distinguishable particles are generally represented by alphabets, for example, A and B. So if there are distinguishable particles in the E4 level of the system, so we will represent it by A and B, so that A and B could be distinguished from each other. So here, when we talk about the microstate of the indistinguishable particles, we say that there are one particle in energy state 3 and one particle in energy state 5. But here, when we talk about the distinguishable particles, so then we say that which particle is there in particular energy state. So the microstate of this distinguishable particle will be like that. The particle A is in the energy state 3, the particle B is in the energy state 5, and rest of the energy state 1, 2, 3, 1, 2, and 4 are empty. How we can also represent it symbolically like this, that the energy state 1, this is empty, the energy state 2, this is empty, the energy state T consists of the particle A, the energy state 4, this is empty, and the energy state 5 consists of the particle B. So this is just a symbolic representation of the microstate for the distinguishable particle. So now we have to discuss that how different microstate correspond to the same macrostate. For example, in the previous figure, if in level 4, one or both the particles change their position, so the microstate would change, but the macrostate would remain the same. That is, we still will have 2 particles in the energy level E4. For example, in the previous figure, we had one particle in the energy state 3 and one particle in the energy state 5. Now, if the particle of the energy state 3 is shifted to the energy state 2, so the microstate is now different. Similarly, if the particle of the energy state 5 is shifted to energy state E4, so the microstate is same. So now we have the same macrostate, but we have 3 different microstates. And similarly, we can construct many different microstates. So it means that for there exists many different microstates to for a single macrostate. Similarly, the microstate for distinguishable and indistinguishable particles are different. So, for example, if we have the distinguishable particle distributed in these energy state like 3 and 5, so we have this microstate. However, if we change, for example, the particle A comes to B and B comes to C, so the microstate will change. However, if they were indistinguishable particle, so you shift one dot to here and the other dot to here, so there is no change in the microstate of the system by shifting the by interchange of the position of the two indistinguishable particle. However, if they are distinguishable, so there is change in microstate of system. Similarly, if you bring other particle C and D to the state, so again this will be another microstate correspond to the same microstate. So it means that the number of microstate for distinguishable particle is more than that for the indistinguishable particle of the same microstate. So if they are just distinguishable particle and they are just dot, so the shifting or bringing another particle will not change the microstate. But if they are the distinguishable particle, so shifting or bringing other particle to the same energy state will change the microstate of the system. So that is why we say that the number of microstate for distinguishable particle is more than that for the indistinguishable particle of the same microstate. So if there are more than one particle in a given energy state, an interchange of the order of particle does not change the microstate. For example, we have two particles in one energy state, or more than one particle, two particle in energy state. So if you change like this is AB and BA. So changing of the order of the particle within the same energy state does not change the microstate of the system. So it means that we could construct a large number of microstate. However, only those microstates are allowed which are consistent with the observed microscopic properties of the system. Such microstates are known as the accessible microstate. And we have a postulate of the statistical mechanics that all possible or accessible microstates of an isolated assembly are equally probable, that each system has the equal probability of occurrence. So this is known as the first postulate of statistical mechanics, or the postulate a priori. So when we talk about the statistical mechanics, so we have an important term of thermodynamic probability, also known as the statistical count. So a thermodynamic probability is the number of equally probable microstate that correspond to a given macrostate. It's called the thermodynamic probability omega of the kth microstate. So the thermodynamic probability of a system is equal to the sum of thermodynamic probability of all the macrostates. So if omega k represents the thermodynamic probability of the kth macrostate, and if there are k macrostate in a system, so the sum of all the thermodynamic probability of the macrostate would give rise the thermodynamic probability of the system. So this capital omega represent the thermodynamic probability of the system, and the small omega with the subscript k represent the thermodynamic probability of the kth microstate. So this means that thermodynamic probability is an odd number. When you talk about the probability and statistic, so this is a smaller number, because when we talk about the probability of occurrence of some event, so that is always in the fraction of 1. For example, a 0.1 or 0.5 or 0.5 means the 50% probability. However, here the statistical count or the thermodynamic probability is a large number, because it consists of the large number of microstates. So this is the main difference between the statistical probability and thermodynamic probability. The thermodynamic probability is a large number. When we have a large number, so then we talk about the average. So there is a second postulate of the statistical mechanics, that observed macroscopic property of the system correspond to the statistical average of its microscopic properties. So we have so many different microscopic properties in large number. So their macroscopic behavior actually correspond to the average behavior of those microscopic properties. So when we talk about the average, so there we have two types of average. One is called the time average and the other is called group average or ensemble average. Ensemble means group or assembly. So a time average is actually observable property of a single system average over a repeated interval of time. So you repeat an experiment again and again, and then you have a large number of reading and then you average it. For example, you have a coin and you toss it. So when you toss it for one time, so you may have head or tail, then you toss it for the second time, for the third time. For example, if you toss it for 50 times, then you may have 20 or 22, for example, the head, and 28, for example, the tail. So then you average it, and then you will have the overall behavior of this tossing. So to find the time average, let's suppose we have NJK is the occupation number of the level J in the macrostate K. And let's suppose delta T is the time interval for each accessible microstate. Delta T is the time interval in which each possible microstate show itself. And then omega K, this is the number of all accessible microstate in the macrostate K. So if you multiply this with the delta T, so it means that this is the time interval for the microstate K. So delta T is the time interval for the microstate and delta T omega K is the time interval for the macrostate. And if we take the sum of all these time intervals, so it will show the time interval of the whole system in which it shows itself in different macrostate, and this whole time is represented by T. So the time average of the occupation number NJK is represented by NJ T. This is the time and this is the bar for the average. So this is equal to NJK multiplied by the time interval for the number of microstate in the macrostate K, and then you sum up all those time interval in which this NJK appear itself, and then you divide it by the total time. So the total time is equal to this value. So you can cancel delta t over here. So you have this value, and then this value is equal to the thermodynamic probability of the system. So the time average of the occupation number NJK is given by this relation. Similarly, we can have the group average, and it is the average property of a large number of replicas of a system taken at one instant of time. For example, if you have a coin and you toss it, so you either you toss it 50 times, then you have to take it the time average. And let's suppose you have 50 coin and you toss it at a single time, and then you have to take the group average. So when you are talking the group average, so there we are talking about the number of replicas. For example, if you have a toss, so there could be head or tail. The head or tail are the microstate of this coin. So how many tails are there and or how many heads are there? So these number of heads or tail are known as the replica. So replica is a copy of the one of the possible microstate. So let's suppose delta n is the number of replicas of an accessible microstate. So delta n omega k will be the number of replicas of the accessible microstate in the macrostate k. And when you sum it, so that will give you the total number of replicas of the accessible microstate of the system, and this we represented by n. So the group average of the occupation number of the jth level, so NGJ average will be equal to, so you NJK multiplied by the total number of replicas of the microstate in the macrostate K, and you sum it. So it is the total number of the replicas of the NJK and the whole system, and then you divide by the total number of replicas. So n is equal to this one, a total one. So delta n could be cancelled, and you have this value, and then you have this relation. So if you remember, so the previous relation for the time average was exactly like this. That is, the group average is equal to the time average, and we take it as a simple average. So if all the microstat are equally probable, the time average of an occupation number is equal to its group average, and we can represent either by nj average. So this was all about the preliminary concept for the statistical mechanics. And in the next lecture, we will talk about the Bose-Einstein statistics. So the Bose-Einstein statistic applies to the indistinguishable particle. It applies to the particle which have integral spin. And this particle with the integral spin fall under the category of boson. And there is no restriction on the number of particles per energy state, that we can put as many particles in a single energy state as we want. That is, they don't obey the Pauli exclusion principle. So inshallah, tomorrow lecture will be about the Bose-Einstein statistics. Okay, thank you so much.